This video is discussing free energy. So we've talked about free energy a little bit before, and that was in our electrochem unit. So free energy is denoted by the symbol delta G. Now, if delta G is negative, what that indicates is that the reaction is thermodynamically favorable. You do want to write this whole word out, thermodynamically favorable. If you're just jotting down notes or practice problems, it's okay just to shorten it to TF. But if you're writing on an actual exam, spell it out, thermodynamically favorable. So if delta G is positive, then that indicates that the reaction is thermodynamically unfavorable. Now, the difference between these two, if a reaction is thermodynamically favorable, that means that it happens on its own. We saw this in galvanic cells. In galvanic cells, the reactions happened on its own. We just put the stuff in there and it went and it made our battery. It gave us some E cell, it gave us some voltage. Also remember sign conventions. If delta G is negative, E cell is positive, K is greater than 1, and that means that the products are favored. If delta G is positive, that indicates that the reaction is thermodynamically unfavorable. What that means is the reaction does not happen on its own. You have to have something to force that to happen. For example, in electrolytic cells, we have to have a power source applied to the reaction in order to get it to work. So the reaction doesn't happen on its own. We got negative E cell values, negative voltages, and we also knew that K values were less than 1, which means that the reactants were favored. So the only thing that can dictate whether or not a reaction is thermodynamically favorable or not is delta G. When we calculate delta G, it needs to be in the units of kilojoules per mole reaction. This is the same unit as delta H. So delta H and delta G are both in kilojoules per mole reaction. We have to pay very close attention because delta S is not measured in kilojoules per mole reaction. It's actually measured in joules per mole Kelvin. So we're going to learn a little bit when we get into all these different types of calculations that we are going to have to pay attention to units. Units is a huge thing here. Sign conventions is a huge thing here. I can't stress it enough. That's where people make their mistakes. This unit overall is quite simple. There's a lot of math involved, but it's very straightforward. But students always make mistakes because they do not make sure that the units cancel out appropriately, and they neglect to transfer sign conventions and things like that. So now that we know conceptually what delta G means, let's talk about the different ways we can calculate delta G. The first one, we've seen this time and time again, is Hess's law. Delta G of the reaction is equal to the sum of delta G of my products minus the sum of delta G of my reactants. So that is Hess's law. If we have those delta G values, we can use Hess's law to solve for delta G of the reaction. Number 2 is a huge equation. You're definitely going to see this multiple times throughout the whole year. This is what they call the granddaddy equation. No, it's not the technical name. I don't remember what the technical name is, but you will definitely see this at some point. What this equation is doing is it's marrying basically delta H and delta S. So it's showing the relationship between delta H, delta S, and how that correlates with delta G. So this is where we have to pay very close attention to units because delta H is measured in kilojoules per mole reaction. T right there stands for temperature, which is in Kelvin, and delta S is measured in joules per mole Kelvin. So we have to pay very close attention because this is in kilojoules, but this is in joules. Now, what are we going to have to do? That means that we're going to have to convert one of these two. Which one do we convert? Well, because we want delta G to be in kilojoules per mole reaction, more than likely we're always going to convert delta S into kilojoules. The way that we transfer joules to kilojoules is we divide by 1,000. Please do not forget that, okay? I stress over and over again, actually plug in your units when you're using this equation and physically cross them out. If you do so, then you'll notice that these units do not correlate, and so therefore you're going to have to transfer one of those rather than just memorizing them, okay? So we're going to have to convert one of these. The best bet is to convert delta S into kilojoules. So pay really, really close attention to that. You're going to have to use this time and time again. For your next type of calculation, that is Hess's law of summation. So we've already dealt with Hess's law of summation with delta H values, and we can also use Hess's law of summation with delta G values. If you remember, Hess's law of summation is where we have the goal equation and multiple equations with multiple delta G values, and it's basically like a puzzle. We're trying to manipulate those equations to make your goal equation. Whatever I do to the equation, I also have to do to delta G. Number 4 we've dealt with before in our electrolytic unit. We have delta G equals negative rat link. Basically, when you use this equation, most of the time you're trying to solve for K. So you're trying to solve for your equilibrium constant. Here's a couple of things you have to pay attention to in this particular equation. Because delta G is measured in kilojoules per mole reaction, this R value needs to be the R value that's dealing with energy. So be sure to use the energy R value. The problem with that, though, is that this is 8.3145 joules over mole Kelvin. And notice how delta G is in kilojoules. So you are going to have to physically convert this R to kilojoules as well in order to make sure our units can cross out. Again, always use and plug in these units in this equation so they will physically cross out. K is what you're solving for most of the time here. K, I like to say, is a little neck of jaybird. What that means is essentially K does not have any units. So you should see that all the units, temperature is in Kelvin. So that's going to cross out with that Kelvin here. Kilojoules per mole and kilojoules per mole, those two are going to cross out. So you shouldn't have any units left in this equation if you're solving for K, which is your equilibrium constant. So pay close attention to that. For the next equation, let me see if I can scroll to the next page. The next equation is delta G equals negative N phi. Some of us did not do a good job with this equation last test. The reason why is they were plugging in everything correctly, but it wanted your unit in kilojoules. And if you'll notice, if you plug in the correct units and physically cross them out, that when you solve for delta G here, you actually get your answer in joules. The reason why, N is moles of electrons. F, Faraday's constant, is coulombs per mole of electron. And E cell is measured in volts. Well, a volt is the same thing as a joule per coulomb. So we have joule per coulomb here. So if we were to physically cross out these units, mole of electrons is gone, coulombs is gone, and we're left with joules. Well, on our test, they wanted your answer in kilojoules. So people just left their answer like that and put kilojoules on there. Well, that's incorrect because you'll have to convert this at the very end. So there are 5 different ways to calculate delta G. Which one you're going to use is based upon the type of information that you're given. So what I want to do with you real quick, I think that you guys might have the math down, but let's just talk about the approach, how we will approach each one of these questions here. So for exercise 4, We want to figure out the delta G value for the reaction, and what we're given is delta G of formation values. Free elements right here are 0, just like delta H, but remember delta S does not have 0 for its free elements. They have an actual value. So if I have a reaction and I have delta G of formations, my approach here is going to be Hess's law. So Hess's law is what I'm going to use for this exercise. That is where I take delta H of the reaction is equal to the sum of delta H of my products minus the sum of delta H of my reactants. And if I have more than one, then I have to multiply that value by my coefficient. So when I do so, you should get a value of positive 59 kilocalories per mole reaction. It's okay to leave this in kilocalories per mole reaction because those are the units that it gave me in the problem, and it didn't specify for me to use anything else. Now the question is, what does this answer indicate about the reaction? Well, because I'm given a positive delta G value, what that is telling me is that this reaction is thermodynamically unfavorable. Now let's look at the next exercise. Let's see, I gotta go back to my mouse, and here we go. Exercise 5. What we're trying to do for this one is we want to calculate delta H, delta S, and delta G using the following data. So we have a reaction here, we have a delta H of formation value chart, and we have a delta S chart. So our approach here is to find delta H using Hess's law. So we would say delta H of the reaction, that's supposed to be a reaction, is equal to the sum of delta H of products minus the sum of delta H of my reactants. And from there, you should get a quantity that's negative 198. Make sure you include units, kilojoules per mole reaction. How do I know what my units are? Is because it's given to me in the data table right there, kilojoules per mole reaction. Now, the question is, what does that answer indicate about the reaction? Since we're dealing with delta H and the reaction is negative, that is indicating that the reaction is exothermic. Now, for the next part, we want to calculate delta S. So we look and see what's given to me. I have different delta S values in my reaction, so I'm going to use Hess's law for delta S as well. So that is delta S of the reaction is equal to the sum of delta S of my products minus the sum of delta S of my reactants. When I plug all these values in, make sure you multiply by 2 and whatnot, then you should get a delta S value of negative 187 joules per mole Kelvin. Now, what does that answer indicate about the reaction? Since it is a negative delta S value, that indicates that I am decreasing my entropy, decreasing my delta S. Now that I have a delta H value and I have a delta S value, how am I going to figure out delta G? Well, since I have both of those values, I'm going to use this equation here. Delta G equals delta H minus T delta S. Now, when I do so, notice when I plug in my units. Delta H is in kilojoules. Delta S is in joules. How am I going to fix that? How am I going to get them in the same unit? That means that I'm going to have to divide this by 1,000 to plug it in. So it's going to be negative 0.187 kilojoules per mole Kelvin is now the units for that. Negative 0.187. Sorry, that's a crazy looking 7 right there. Kilojoules per mole Kelvin. So I'm going to plug that in for delta S. Temperature, I'm given my temperature right there is 25 degrees Celsius, but I could potentially not be given that temperature right there and still know exactly what the temperature should be. What gives it away is this little knot symbol that you see there. You see the little knot symbol at delta H, the little knot symbol at delta S, and the little knot symbol of delta G. That little knot symbol means that we have 25 degrees Celsius there. And 25 degrees Celsius translated into Kelvin is 298 K. So now that we have delta H in kilojoules, temperature in Kelvin, and delta S in kilojoules per mole Kelvin, we now can plug all of that stuff in and solve for delta G. So when you solve for delta G, you should get negative 142 kilojoules per mole reaction for your answer there. Now, the question is, what does that indicate about the reaction? Well, that indicates that my reaction is thermodynamically favorable, that the reaction happens on its own. So we have a reaction that's exothermic, that's decreasing in entropy, but it is thermodynamically favorable. Now looking on to exercise 6, let's see what we're given here. So we're given multiple reactions, multiple delta G values, and we're given a goal equation. So our approach here is to use Hess's law of summation. So we have to figure out what we need to do to manipulate these equations to solve for my very last one. So Hess's law of summation is our approach from this one. If you do this correctly, you should get negative 3 kilojoules per mole reaction. Now let's look at the last one we're going to work on today. That's exercise 7. Let's see what this is asking. Exercise 7 says that we want to figure out the equilibrium constant. So, based upon the data below. So we have a reaction. We want to find equilibrium constant. So we know that we're going to have to fuse delta G equals negative Ratlink. So RT natural log of K. But the problem is they're not giving me delta G values. So what are we going to have to do? Well, our approach 1, we have delta H values. What we can find from there is my delta H of the reaction using Hess's law. Step 2, I have delta S values. Well, what I can find from there is delta S of my reaction using Hess's law. Once I know delta H of the reaction, and I also know delta S of the reaction, I can solve for delta G by using that delta H minus T delta S equation. Remember, we have to make sure units comply. Units, units, units. So what are we going to have to do? Because this is in joules per mole Kelvin, and this is in kilojoules per mole, we're going to have to convert my delta S into kilojoules to plug it in right there. Now, once I know my delta G is going to be in kilojoules per mole reaction. Remember how we talked about the R value that I use here is 8.31. That is in joules per mole Kelvin. So these units, again, do not match up. So what I'm going to have to do there is make sure that they match up by converting one or the other. It doesn't matter which one you convert, whatever you feel more comfortable with. Me personally, I like to convert my R value. So that would be 0.0085 0.31 kilojoules per mole Kelvin. And remember, that's a negative quantity right there. So what I'm going to do is I'm going to take my delta G value, divide it by negative RT, and that gives me natural log of K. To get K by itself, remember that natural log turns into E, and I fishhook whatever that answer is. So it's essentially E raised to the delta G over negative RT is equal to my K value. It is totally okay once you get this value right here as an answer to say E raised to that number is equal to K. That is a perfectly acceptable answer. I think what I calculated when I got I got E raised to the 601 is equal to K. Now, when I physically put that in my calculator, that number was so large that it gave me like 0 as my K value, or it says, it won't say 0, it'll say error, or it'll say overflow because it's such a huge number, 10 raised to the 261. So if your calculator says overflow, under, or error, or 0, then it's totally acceptable to leave your answer like this, and it would be valid. They would give you full credit there. So we went through delta G and how to do some of the calculations with that. Hopefully this will help you for your problems that you're going to be doing in class. We still have a few more topics to cover here and there, but this is the bulk of the unit, and so hopefully you're doing well with it so far.